A 5-meter radius playground merry-go-round with a mass of 160 kilograms is rotating freely with an angular speed of 1 radian per second. 2 people, each having a mass of 60 kilograms, are standing right outside the edge of the merry-go-round and step on it with negligible speed. What is the speed of the merry-go-round right after the 2 people have stepped on? Okay, so this is like a collision question where the 2 people collide with this merry-go-round, except the merry-go-round is rotating. So it's a rotational collision question. So we're going to be looking at rotational momentum. Since there's no external torque acting on the system, the angular momentum of the system will be conserved. So I'm going to say angular momentum, which is the letter L, that's the variable, total initial is equal to L total final. Okay, so we have 3 different objects. We have a merry-go-round and we have 2 people. Okay, so I'm going to say the initial momentum of person 1 plus the initial momentum of person 2 plus the initial momentum of the merry-go-round is equal to the final momentum of person 1 plus the final momentum of person 2 plus the final momentum of the merry-go-round. Okay, so there's 2 different formulas that we use for angular momentum. So for linear momentum, we had this formula. Linear momentum equals mass times velocity. For angular momentum, L, we have the rotational equivalence, which would be I times omega. Okay, so now when we're talking about a rigid body, the I depends on the shape of that object. So when we're talking about the merry-go-round, angular momentum of the merry-go-round, okay, then the I is the moment of inertia of a disk, okay, and that would be a solid disk. So the moment of inertia of a solid disk is 1/2 mass of the merry-go-round, radius of the merry-go-round squared, times that omega. When we're talking about the people, though, we're going to treat those people like they're just particles. So the L of 1 or the L of 2, okay, they're both the same. We can still think of it as I times omega, but the I, the moment of inertia of a particle, is mr squared. So now we're talking about the person times omega, where r is the distance from where that person is to where the axis of rotation is. Okay, so if we were to think of what this looks like, here's the merry-go-round, a person steps on from a point right onto the edge of the merry-go-round. So the distance between the axis of rotation, which is the center of the merry-go-round, to that actual person, which is on the edge of the disc, is just the radius of that merry-go-round. Okay, so it's the same r as we did up above over here. Okay, now omega, when we're talking about the angular momentum of the person, before they jumped on the merry-go-round, they were not rotating. So we don't want to use omega to describe their motion, but we can use this formula, V equals omega r, and solve for omega to get V over r. And now that's what we're going to use instead. So I have mr squared V over r, and notice that the r's cancel out. So now I have mrv. Or as it's written usually, it's rmv. Now since the person jumps on the merry-go-round so that they are perpendicular to that r vector, the r vector going from the axis of rotation to the point where that person is, they're jumping on this way, that's their velocity vector, and the r vector is this direction. Those 2 vectors are perpendicular to each other. Normally we would write sine of the angle between the 2 vectors, but since that angle is 90 degrees, sine of 90 is just 1, and all of that just goes away. So I'm just left with rmv. Okay, now in this question, they tell us that their speed is negligible, so that v is actually 0 for their initial momentum, angular momentum. So the whole thing just goes away. So the angular momentum of each of those people is just 0. So let's put in the formula for the angular momentum of the merry-go-round initially before the people jump on. So it would just be 1/2 mass of the merry-go-round, radius of the merry-go-round squared, times omega. Okay, and we know the omega is right here. So this is my initial omega. I'll put an I for initial. Now, once the people jump onto the merry-go-round, they're stuck on it. So this is like an inelastic collision. So I'm going to say I total times omega. Okay, now my I will be the I of the first person plus the I of the second person plus the I of the merry-go-round times omega final. And we're looking for the speed of the merry-go-round right after the two people have stepped on, not the angular velocity. So we're going to have to use this equation again over here to change the angular velocity into the speed. Okay, so I'll do that in the next step. So I have 1/2 mass of the merry-go-round, radius of the merry-go-round squared, times angular velocity of the merry-go-round. I'm keeping that as an angular velocity because that's what's given to me, equals the moment of inertia of the first person. Now we're treating them as particles, so it'd just be mr squared of the first person plus mr squared of the second person plus the moment of inertia of the merry-go-round is 1/2 mass of the merry-go-round r squared. All of that times the final angular velocity, which we're looking for the final speed, so we're going to change that over to v over r. Okay, all of these r's are the radius of the merry-go-round. So we can see that one of those r's can be canceled with the r that's on the bottom. So I'm going to do that right now. So I'm going to cancel one of these r's with the r on the bottom. Okay. I can also see that the mass of the merry-go-round is not in each of these terms, so I can't just go canceling them out. But now I have an r of the merry-go-round squared here, r of the merry-go-round, r of the merry-go-round, r of the merry-go-round, so I could cancel one of those off again. So this is going to cancel with this, this, and this. So I'm dividing them all out. Okay. So now we're trying to solve for this v over here. So we're going to rearrange our formula. So we have 1/2 mass of the merry-go-round, radius of the merry-go-round, omega initial, divided by m1 plus m2 plus 1/2 mm is equal to v. And this is my v final. So v final is equal to 1/2 mass of the merry-go-round, which is 160 kilograms. Radius of the merry-go-round is 5 meters. Initial angular velocity is 1. Mass of the person, each person is 60. So 60 plus 60 plus 1/2 times the mass of the merry-go-round is still 160. And now I'm going to just plug everything onto my calculator. And I get exactly 2. Okay, so now if I look at significant digits, I have 3 here, I have 3, I have 3, and I have 3. So my answer should also have 3. So I'm going to write 2.00 meters per second. And that is the speed of the merry-go-round right after the two people have stepped on. Thanks for watching.